Okay, here we have a rock being lifted out of a lake by a rope. So the rock is an important object. The rope is an important object. Whatever, hand or winch or whatever is pulling it out is interacting with the rope. The earth is important. And actually the water is important here too, because we've been told that there's a drag force that's exerted that's going to be significant. So we don't usually take into account fluid resistance, but then again, we're usually in the air rather than in the water, and drag is definitely more significant in the water than it is in the air. So let's take care of that one first. We're saying that the rock and the water are having this interaction. You can call it F drag. You could call it, in some ways, it's a normal force, not entirely explainable by that, but if you think of the rock pulling up and it hits all those water molecules, and that's a large component of that is normal force. The hand and the rope and the rock, that's tension. The hand's touching other stuff, but we're not going to worry about it. Water's touching other stuff, but we're not going to worry about it. We really care about the rock. So we want to make sure we get all those interactions in. There's definitely weight between the rock and the earth. And again, earth is interacting with more stuff, but we really only care about the rock. So we have all the interactions for the rock. We can draw a free body diagram. So we have tension going up. We have the drag going down, opposing the motion. We have the weight going down. So there's a drag force. It's actually pretty small relative to the weight if you look at the numbers. And then the tension is pulling it up. Now, I drew this balanced. Pretty close to balanced at least. Why did I draw it balanced? Well, it's going upward, sure, but it says constant speed, which means the acceleration is 0. So you got to be always on the lookout for constant speed. That should be a big alarm going off in your head that says the forces are balanced. If I take positive upward, I have the tension going upward, the drag going down, and the weight going down, and it is going to equal 0 because it's in CVPM. So at this point you can either solve symbolically or plug in numbers if you want. I'll go ahead and do it symbolically, I guess. Alright, so I'm going to add this mg over to the other side. I'll add the F drag to the other side. So there I am. The mass was 50 kilograms times 10 newtons per kilogram. The weight. The drag is 30 newtons. So that's 500 newtons plus 30 newtons. So the tension in the rope is 530 newtons. If I wanted to lift it up faster, if I wanted to accelerate it up, I would have to pull with more than that so that the forces would become unbalanced and the acceleration would go upward. If my tension drops below 530 newtons, it's going to start to slow down because the lower forces are going to be bigger than the force going up, and the acceleration will be down. Velocity will still be up for a little while, but the acceleration is down, which means we are slowing down.